Hello, welcome to the third and final part of section 8.4, other convergence tests. So here I'm going to go over the ratio test and the root test, okay? Now first, the ratio test. The ratio test tells you that if you have the series that goes sum from n equals 1 to infinity of an, if you take the limit as n goes to infinity of the absolute value of the ratios of an plus 1 an, and you get some limit less than 1, then the series is absolutely convergent and therefore converges. If you take the limit as n goes to infinity of an plus 1 over an, and you get something larger than 1, then the series is divergent. And if you get exactly 1, then the test is inconclusive. You have to do something else, okay? Now, this test, it's good when you have when you have exponential functions, when you have factorials, when you have things that when you take two consecutive terms, you can cancel some things. So for example, check this out. Determine if the series is absolutely convergent, and we have negative 1 to the n to the fourth over 5 to the n. See, you have a bunch of exponents, and we're going to be able to cancel a bunch of things when we take the limit as n goes to infinity of the absolute value of the ratio. Okay, so let's do this. So we're going to take the limit as n goes to infinity of an plus 1 over an, the absolute value of that. So this is the limit as n goes to infinity of, well, if this is my an, then an plus 1 is just negative 1 to the n plus 1, n plus 1 to the fourth over 5 to the n plus 1. And then I'm going to divide by an, but dividing is the same as multiplying by the reciprocal. So I'm just going to do it here. I get 5 to the n over negative 1 to the n, and then n to the fourth. And there are a lot of things that we can simplify here, okay? For example, here I have negative 1 to the n plus 1 and negative 1 to the n. I'm left with negative 1. I'm left with the limit as n goes to infinity of the absolute value of negative 1. Then I can combine this n plus 1 to the fourth and this n to the fourth, write it as n plus 1 over n to the fourth. And then what else? Then here we know that this is just 5n times 5. So I can cancel 5n with 5n, and I get 1 over 5, okay? I can simplify this even further. I'm taking the absolute value. So this is just 1 over 5 times the limit as n goes to infinity of the absolute value of n plus 1 over n to the fourth. And here the absolute value is a continuous function. The fourth, right, raising something to the fourth power, this is also a continuous function. So I can take that limit inside. I'm going to take this with me. And we can take this inside, okay? So what I'm saying is that this is just equal to 1 over 5. And then the absolute value of the limit as n goes to infinity of n plus 1 over n, this whole thing to the fourth, which is just 1 over 5. And then the limit as n goes to infinity of n plus 1 over n, that is just equal to 1. So this is just times, I'm going to say times the limit as n goes to infinity of n over n. This is just 1 over 5, okay? Perfect. So that tells me that since this is less than 1, we can say that our series converges. Therefore, the sum from n equals 1 to infinity of negative 1 to the n, and I already forgot, n to the fourth over 5 to the n converges. Actually, we know that it absolutely converges, but if it absolutely converges, then it converges, okay? What else do we have? Test the convergence series, test the convergence of the series n to the n over n factorial. So let's see, what do we have here? Let's do the same thing. We take the limit as n goes to infinity of the absolute value of an plus 1 over an, where this is an. So we get that this is the limit as n goes to infinity of, here we have n plus 1 to the n plus 1 over n plus 1 factorial. And then we can simplify this thing again. And well, dividing by an is the same as multiplying by the reciprocal. So we get n factorial over n to the n. So what can we do here? What can we do? Well, let's see. I can do a lot of things. So limit as n goes to infinity of, I can write this n plus 1 as n plus 1 to the n times n plus 1. And then the denominator, n plus 1 factorial, I can write as n plus 1 times n factorial. And then the n factorial here stays like that, and n to the n also stays like that. But now I get to cancel n factorial and n factorial, n plus 1 with n plus 1, and I am left with the limit as n goes to infinity of the absolute value of n plus 1 over n, the whole thing to the n. Well, this is the same as the limit as n goes to infinity of, and you can even simplify this thing if it's easier for you to see what's happening. 1 plus 1 to the n, and then to the n. As n goes to infinity, this goes to 0. This goes to infinity, so you get something of the form 1 to infinity. Hopefully you're looking at this and you recognize that this is the definition of E. If you don't recognize it, then L'Hopital this thing and you get that this is just E. Well, E is equal to 2.71 something something larger than 1. That tells us that this series diverges. So sum from n equals 1 to infinity of n to the n over n factorial diverges. Interesting. Okay, what else do we have? What else do we have? We have now the root test. Consider the series sum from n equals 1 to infinity of a n if we get that the limit as n goes to infinity of the nth root of the absolute value of a and it's equal to L less than 1, then this series is absolutely convergent and therefore convergent. If it is larger than 1, then it diverges. If it's equal to 1, it's inconclusive. And this is very important, okay? If either the ratio or the root test is inconclusive for series, then the other will be as well, okay? In other words, if you try the ratio test and you get that the limit is equal to 1, do not try the other one, okay? Okay, perfect. So then this is not this is okay, perfect. So test the convergence of the sum from n equals 1 to infinity of 4n plus 5 over 7n plus 2 to the n. Okay, so check this out. We have the limit as n goes to infinity of the nth root of the absolute value of an. This is just so that when we take that nth root, we don't have to worry about what we get inside, what's left when it comes to signs. So this is just the limit as n goes to infinity of, well, 4n plus 5 over 7n plus 2 to the nth power. And we take the nth root of that, 1 over n. So we're left with the limit as n goes to infinity of 4n plus 5 over 7n plus 2. This is equal to, I can take the quotient of the leading terms. So n goes to infinity, 4n over 7n. I get 4 over 7. This is less than 1. And the fact that I got that the limit of the nth root of the absolute value of an is 4 over 7 less than 1 tells me that, conclusion, this series is absolutely convergent, therefore convergent. So, therefore, the sum from n equals 1 to infinity of 4n plus 5 over 7n plus 2 to the n is absolute okay, absolutely convergent and therefore convergent. Okay, awesome. This is all I have. Okay, this is all I have for section 8.4. I hope everything makes sense. See you next time. Bye-bye.